So what should we be aiming for? More recent construction methods are modular construction. Entire buildings made from modules or pods. Core of the structure is made from reinforced concrete, heavy gauge steel, structural timber, etc., and is done on site. Structure of the pods is made from light gauge steel or timber battens, i.e. wall panels, roofs, floors. Services are built into the pods during the manufacturing process. Finishes are completed in the factory, i.e. bathroom tiles, floor tiles, etc. This means that one pod just needs to be installed on site, and this section of the building is ready for use. 2. Excellent quality control. Manufacturing of the building in the workshop means that the possibility for mistakes between various contractors, structural, mechanical, electrical, etc., has been radically reduced. For example, if a column is in the line of a service duct in a regular building, the duct would either need to go around the column or through it. This potential problem has been eliminated by using modular construction. Waste generated during the construction process has been reduced due to the complete construction process being completed in a factory environment. Any offcuts or additional unwanted material can be recycled at the production stage instead of accumulating large quantities of waste on site. Environmental, social and economic risks are greatly curtailed. Completing the construction process in a factory environment means that there are a lot more controls can be put in place to delivering a more sustainable development. Environmental improvements for the project are reduce waste, transport emissions, noise, dust, dirt, pollution, etc. Societal improvements are made by eliminating the large quantities of delivery trucks to daily site, interrupting the social surrounding of the neighbourhoods, e.g. shopping centres, hotels, schools. It is common for pods to be delivered during the night so that little interruption is caused to the local roadways and walkways. Economical risk, the only variable is raw material costs and availability. Everything else should be very well estimated financially speaking, i.e. employment, transport, permits, etc. Number 5, construction program. This is becoming a dominant construction method for fast-paced developments. A lot of work is required in the initial design, programming stage, but once this is complete, the project can be delivered once the site is ready for the pods to be installed. And number 6, almost full strength is achieved after installation of the pod or module. So, modern construction methods. A case study, this picture shows the Marriott Group with a new development in New York City. 50% of the US hotel developments have now gone down the modular route due to a radically reduced construction time. Cost is another major factor that influences this drive for modular construction, with the Marriott saving $30 million on their new AC Nomad Hotel in New York by going for this method of construction. So, sustainable supply chains for prefabricated house building. Code critical factor required by relevant content mentioned by prefab experts. 1, competitive price setting, thin profit margin distribution, high price of materials with fewer options, maintenance and serviceability costing inclusion, no life cycle value consideration, bespoke nature of products required for the premium product with precision and high quality. Cost, CF9, skilled worker shortage, lack of prefab vocational education, poor mechanisms for salaries, employee retention, lack of prefab experience, lacking skills to manage off-site and on-site issues. Cost, economies of scale, demand uncertain, lack of bulk demand, uneven order flow, delay in order processing. And finally, intensive capital investment. Huge investment is an intellectual property, marketing costs to promote the building system, high setup costs, expensive design production software packages with annual licensing fees, and limited return on investment. In terms of quality, complex consenting process, parallel processing of building consent and process inspections, quality assurance, lacking cross-reference to offshore building codes for compliance, higher dependency and costing due to outsourcing, usability of multi-proof, complex and strict council building regulations. Next, high on-site engagement, communication issues between yard construction and on-site installation, more efforts on-site preparation, design and production errors. Unoptimized and less precise manufacturing, unoptimized manufacturing output, integration between design, procurement and manufacturing, material selection, that's on downsized chain dependency, horizontal and vertical dimension limitations of products. And finally, inadequate offshore facility, poor factory layout, production line disturbance, off-site storage issues, off-site health and safety issues, local market accessibility. Now, when it comes to features, lack of access to financial solutions, restricting bank financing, meagre financing solutions, lack of government incentives, on-site cranage constraints, health and safety risks in terms of lifting, on-site connectivity issues, appropriate lifting mechanisms, high cost of cranage and outsource risk, and finally for delivery, unavailability of technical support, slow development of prefab standards, lack of standards and codes, lack of technical support, and poor quality system, limited R&D programs. I'm still recording. So, for international competition under innovativeness, risk of overseas product intervention with innovative and high quality solutions, local industry monopoly and cartels, volatile market situations due to economic unrest, inappropriate business strategies, lack of sustainable market, difficulty in aligning product, process and organizational goals, lack of knowledge about business model innovation, entrepreneurial and leadership needs, and slow adoption of advanced digital technologies, limited use of resource planning software packages, complex design and detailing software packages, limited awareness about BIM and its usability. Now, for poor delivery systems with longer lead times, logistic capability issues, long lead times, dependency on traditional delivery methods, durability and quality problems during transportation, on-site constraints and lacking just-in-time. On-site cranage constraints, health and safety risk in lifting, on-site connectivity issues, appropriate lifting mechanism, high cost of cranage and outsourcing, and finally poor off-site payment mechanism, pay on time or pay interest, credit-based contracts, lack of the security of payment, lack of bespoke procurement process. And finally, when it comes to flexibility, high design variability, varied customer requirements, frequent changes in orders, technical and design issues, and lacking resilience capabilities, unstable cash flow to run the business, overheads and maintenance cost of a budget, income and tax variations, effects by natural or man-built disasters, and lacking multiple business profiles and flexibility. So these are some of the supply chain challenges that would be applicable in New Zealand. Product life. So moving on to the next phase of the life cycle assessment, how can the development be made more efficient for its entire life cycle? Examples of where an engineer can enhance a development life cycle efficiency: achieving larger open spans, space efficiency, for example, post-tension concrete, incorporating energy systems, solar, wind, etc., water recycling measures, using easily maintained materials, enhanced natural lighting, and green roofs, bringing green sites back to the city. So taking a closer look, floor space. How can we increase the rental floor area available for a lease? Common new methods are to try to reduce the internal columns in a building. This can be done through a hybrid main structural system, diag rods and concrete core, where the system carries the vertical and the horizontal actions. Another method is to use advanced floor systems, post-tension floor slabs, column centers up to 20 meters, center to center, or composite floor systems, secondary spans up to 18 meters. Number 2, energy systems. Take advantage of the development of your building and think outside the box. Sustainability is a topic of continuous further research and is open to endless possibilities. Examples could be to introduce an energy harvesting system into a busy office swivel door, or install transportable solar panels as the facade, etc. Number 3, enhance natural lighting. A common method of increasing the natural lighting in a building is to use glazing for the facades of the building. It is also an option to glaze the core if large openings are present in the core. In providing comfort to people inside the building, a visual deterrent or fogging of the glazing to a specified level by the architect is commonly provided, i.e. shopping centre changing rooms would need complete fogging. Number 4, low maintenance materials. For a surface that is going to receive a lot of contact from the users of the building, it's common to design this surface as a low maintenance surface. For example, door handles are almost always stainless steel to prevent stains accumulating, and also because it is an easily cleaned surface. In contrast to this, if fake grass or astroturf is used in a restaurant floor, it may be more difficult to clean if food or drink was spilled on it. So try to think sustainable for the life cycle process as well as for the design process. 5, repetition. Don't have a structure that is detailed differently just for the sake of it. If an identical detail fulfills the structural demands in many locations, use it. Future problems can be easily dealt with if the structure is quite common throughout. By having a repetitive structure, it also curtails confusion on site with all different fixings that need to be constructed. And finally, number 6, green roofs. Try to incorporate as many green roofs as possible to make our cities green and green. This will help absorb some of the carbon dioxide that has been released due to the built environment. End of life. Our current system for end of life is take, make, waste. This should not continue, and we need to perhaps think in terms of a circular economy. Sustainability needs to be a journey for all of us. How can we plan and manage a sustainable life cycle? Structural health monitoring could be incorporated into BIM for life maintenance, repair schedules, economic analysis from the initial stage, spend money on day 1 or over the life cycle, structural strengthening to enhance structural capabilities, fibre reinforced polymers, environmental risk assessments at the end of life, government buildings versus hay sheds in the countryside, and think about demolition. How can the building be reused, repurposed, etc.? So, structural health monitoring in New Zealand can provide clients with a better view if their development needs maintenance, upgrading, or demolition. It also allows accreditation bodies to examine if a structural development is on target for its standard. Another reason to use structural health monitoring is to protect the surroundings. For example, in the shopping centre, you need maximum safety for the members of public present. This doesn't need to be as stringent for the like of a hay barn in the countryside. Economic analysis at initial stages. These are being carried out to examine the life cycle duration that is being targeted for. This may be fulfilled through some various options, e.g. initial design investment versus mid-life upgrades. Economic analysis at the initial stage to examine what the most suitable option for the client is. Maybe spend a lot of money on day 1 and cut out the maintenance costs through its life cycle, more certainty even with fluctuating interest rates. So this is probably the most favourable option. Number 2, reduce initial costs and set time interval maintenance upgrades to keep development safe and functioning for its entire life cycle. Or number 3, spend as little as possible to be compliant with building regulations and maintain this standard for its entire life. So this one would be the least favourable option. So structural strengthening, FRPs, fibre reinforced polymers can be used in the strengthening of repair of structural elements. For repurposing developments where additional floors are being constructed, FRP can be used to strengthen column capabilities. Economic risk assessment at development end of life. This is the development still legally covered under the design codes building regulations that were used 50 years ago? Ethical behaviour by the client is important here. What is at risk? Comparing an old apartment block with 1,000 residents to a portal frame shed in the countryside, what can go wrong in each case? Cost-benefit analysis. What is the financially viable thing to do for the client? Incentives available to the client. Is the government offering incentives for retrofitting an old building instead of demolishing and rebuilding? Attracting external investment. If demolished and rebuilt, will it attract new investors to an area? Urban regeneration. So, redevelopment of the site or demolish. Factors to consider if a client is going to rebuild instead of retrofit. Carbon emissions for demolition, production phase, construction phase, life cycle phase of the new development instead of retrofitting existing buildings. Demolition material. Can material be reused or will it be going straight to a landfill? If it's going to a landfill, it might be better just to retrofit. Pollution to surrounding areas. A city centre site with hotels, school and government buildings surrounding site, it will cause a lot of noise, dust, etc., pollution for local businesses. And finally, business interruption. If clients decide to rebuild, businesses will close for a long duration. There'll be problems. Customers, competitors, reputation, reliability as a business. So, building information modelling is therefore an essential skill for all engineers, and these are some of the training resources from some of the different institutions that are available. So let's have a closer look at New Zealand. As we saw earlier, New Zealand is ranked 5th in the world for its greenhouse gas emissions. Breaking down New Zealand's greenhouse gas emissions, for a population of 4.8 million, we've got an extremely greenhouse gas level. Industrial agricultural business is the key leader in releasing greenhouse gases. 1 tonne of methane is equivalent to 28 tonnes of CO2. As for the built environment, fuel combustion, internal processes and product use, waste are all applicable. From now, to analyse New Zealand, we're going to break down the life cycle assessment into 3 main sections. Production phase, raw material, extraction, material processing and part manufacture. The construction phase, which would be assembly, and the life cycle phase, product use and end of life. So, using the carbon footprint as our main comparative, definition, sum of greenhouse gas emissions and removals in a product system expressed as CO2 equivalents, and based on the life cycle assessment using the single impact category of climate change. And that's a quote by Vickers et al. From 2018. So carbon footprint breakdown in New Zealand for the production phase. Raw material extraction, material processing, part manufacturing only. Looking at the built environment, 5% of New Zealand's carbon footprint is caused by the production of construction materials to allow development works to go ahead. This only includes the materials that have been produced for New Zealand-based developments and does not consider materials that have been produced for export.